So welcome. We had seen some problems in the last class. Make sure that you're able to do all these problems. Make sure you understood them. Some more problems we will do. There are 2-3 more concepts that we are going to do, but we are going to demonstrate, or we are going to look at those concepts through the help of problems. So just to refresh your memory, we are on mass transfer. We are doing these two parts together. Just to help you remind you of all the things that we have in the last class. What methods can we use for estimating the value of mass transfer coefficient? Just tell the names of the methods. We will see more in detail in the next class. Which methods did you use in the previous problems? Did you use empirical? Did you use theories? Did you use analogies? What is the physical significance of Sherwood number? We talked about that. What is a Frostling correlation? Where is it used? These are the equations that we have used for microscopic balances. This is the strategy that we are adopting. Either macroscopic or microscopic laminar or microscopic turbulent. Okay, we saw one problem first and then the other problems we saw here. Let's go forward. Little bit about mass transfer coefficient. Just to remind you. So for liquids we can write flux is equal to KL multiplied by delta CA. Concentration driving force, we are going to call this as liquid side mass transfer coefficient, and rate of mass transfer, if we write in terms of kilomoles per second, KL will be in terms of meters per second. Now for gases, flux we can write in terms of concentration. Flux we can write in terms of the driving force, we can write either in terms of concentration or we can write in terms of partial pressure. So flux, if you write in terms of Na, in terms of partial pressure driving force, then the unit of kg would be kilomoles per meter square per second or Pascal. Okay. Partial pressure driving force, right? And then the rate of mass transfer would be kg into A into delta Pa, driving force, partial pressure driving force. We can write concentration driving force. If I divide by RT, multiply by RT, we can get kg into RT divided by delta Pa by RT. That's nothing but delta Ca, concentration driving force. And then this kg prime would be related to kg multiplied by RT would be this kg prime, and then this kg prime would be in terms of meters per second, like for liquid side. Okay. So just little bit more about mass transfer. So sometimes we are going to have both mass transfer in the liquid side as well as gas side. So that's why we are using the subscript KL and kg. Okay, let's go forward. Here's the problem. Consider that the air is flowing in a 25 millimeter pipe at a velocity of 15 meters per second. So imagine the situation. Pipe is there, right? Air is flowing in that pipe at a velocity of 15 meters per second. For this problem, assume that air density is this constant 1.2 kg per meter cube. Viscosity is constant 2 × 10 - 5 pascal second. Let's assume that this air contains some pollutant. So concentration of the pollutant at the inlet of the pipe is, let's say, 1000 micrograms per meter cube. Walls of the pipe are coated with a catalyst that destroy this pollutant. And assume that the rate of destruction, rate of reaction that destroys the pollutant at the pipe wall is so fast that concentration of pollutant at the pipe wall can always be considered to be zero. There's another important concept coming. Diffusivity of pollutant in the air is 10⁻⁻⁵ meters square per second. So three-way catalytic converters work in this principle. They destroy the pollutants, NOx, carbon monoxide, and unburnt hydrocarbon. Okay, what I would like you to calculate is the length of the pipe required to reduce the concentration of pollutant from 1000 micrograms per meter cube to 10 micrograms per meter cube. Solve this problem. Think about how you're going to solve it. Okay. Pause the video, think. Let's go forward. Here's the solution. So rate of reaction is very fast. So concentration of the pollutant at the pipe wall can be always considered to be zero. So that means there is, if this is a pipe, if you visualize a pipe, let's say pipe is like this. Okay. Pollutant is going in the pipe, but at the surface of that pipe, concentration of the pollutant is zero. So there is a driving force for that pollutant to go from the bulk of the air to the surface of that pipe. That's where concentration is zero. That's where mass transfer is occurring. let's visualize it further. So this is an airflow. This is a pipe. So at the inlet, concentration is 1000. At the outlet, concentration is 10. That's what we want. We want to find out the length required. Air velocity is 15 meters per second. So volumetric flow rate, if you calculate, it is 7.36 into 10 raised to minus 3 meter cube per second. And so Reynolds number for air in the pipe, if you calculate d v rho by mu, it will be 22,500. Highly turbulent. Highly turbulent. So do you want to use this? Obviously we can't use this. Do you want to use this? I don't want numerical solution. We don't want to do 3D. We don't want to solve partial differential equation. Let's use macroscopic balance. Okay. Think about this concept now. Imagine that concentration incoming is 1000. After some distance it becomes 900, 800, 700, 600, 500, 400, 300, 1200, 300, 200, 100, 10, 9, 8, 110 and so on and so forth. 90, 80, 70, 10. So that means if you think about the driving force is 1000 minus 0 here. Somewhere it is 900 minus 0, somewhere it is 800 minus 0, somewhere it is 700 minus 0, somewhere it is 600 minus 0, 500 minus 0, 400 minus 0, 300 minus 0, 90 minus 0, 80 minus 0, 70 minus 0. So driving force is all the time reducing. In the previous problems, driving force was changing with respect to time in the sugar dissolution problem. Now driving force is going to change with respect to distance. So what I will do is I will consider a small differential element of thickness delta z at a distance z from the inlet of the pipe, z and z plus delta z, and we'll write this as a control volume and we'll write mass balance on this control volume. Okay, here's another concept. If you look at this, if you look at any location here with respect to distance, concentration is 0 at the wall and concentration is higher at the bulk of the pipe, say center of the pipe. So there is a concentration driving force. So there is a laminar sublayer, boundary layer, there is a buffer layer, there is a turbulent core, and then we call this as a boundary layer, concentration boundary layer. So visualize all this. So if you think about this, let's say this is our pipe. We are looking at cross section, right? This is our boundary layer, laminar sublayer, viscous sublayer. Let's say this is our boundary layer. Don't worry about the value of that boundary layer. What is the value? Just imagine in the bulk of the pipe, it is almost constant. Okay. So let's say concentration somewhere here. Let's say we are saying somewhere here. Let's say is 500. Okay. At this wall of the pipe, concentration is 0. At this wall of the pipe, concentration is 0. Okay, inside wall of the pipe, obviously it is going outside, but that's because I'm trying to draw. So there is a driving force for mass transfer. So whatever pollutant, whatever A is there, it is transferring, it is getting transferred from the bulk through this boundary layer to the surface. It is getting transferred here. It is getting transferred. What is happening at the surface of this pipe? This pollutant is reacting and it is making 0. Now these two are steps in series. You see, pollutant is going to the wall and pollutant is getting consumed at the wall. Pollutant is going to the wall and it is getting consumed at the wall by way of reaction. Imagine that instead of this pollutant, let's say is a food, and at the wall, let's say you are sitting, you are very hungry. So there is mass transfer of food from the kitchen to the dining table and you are consuming at the dining table. Visualize. 2 steps in series: transfer of food from the kitchen to the dining table, consumption of the food by you. You are extremely hungry. You eat the food at a very rapid rate. What happens? As soon as the food comes, you have gulped it down. Concentration of the food on the dining table is 0. Whereas now if mass transfer was very high and mass transfer of food from the kitchen to the dining table was very high and its consumption was very low by you, food will just accumulate on the table. Right? Two steps in series. Two steps in series. Transfer to the wall and consumption at the wall of the pollutant in this case. So therefore, concentration, because the rate of reaction is fast, concentration of the pollutant at the surface is 0. So the driving force in this particular case at this particular location is 500 minus 0. Somewhere else it is 400 minus 0. Somewhere else it is 300 minus 0. Somewhere else it is 600 minus 0. Somewhere else it is 800 minus 0. Somewhere else it is 990 minus 0. Visualize. Pause the video. Solve this for yourself now based on this information. Here is the solution. Right? We are going to write mass balance for this pollutant in this control volume. So mass in, material in, rate of mass coming in is Qg multiplied by C at Z. Volumetric flow rate multiplied by concentration per unit volume. It is what is coming in at this control volume here. What is going out? Qg multiplied by C but evaluated at Z plus delta Z. So this difference in minus out is what has reacted. How much it has reacted? It is equal to what has been transferred. You are consuming at as fast as it comes. So rate of reaction, it is consumed at the rate of reaction at the wall. It is the same as rate of mass transfer to the wall. So Qg into C at Z minus Qg into C at Z plus delta Z is equal to Kg prime, mass transfer coefficient in terms of meters per second, A into delta C. We are writing concentration in terms of moles per unit volume, not partial pressure. What is the surface area? Surface area is this surface area. Surface area where the mass transfer is occurring. Pi multiplied by d, that's the perimeter, multiplied by delta Z. C minus 0. Okay, so you get minus Qg dc by dz is kg prime pi d into C. Integrate. Straightforward. How do I get kg? Macroscopic approach. So I have to use some kind of equation. That equation in this particular case is Sherwood number 0.023, Reynolds number is to 0.83, Schmidt number is to 1 by 3. If you want to see this equation number 3018 from Welty's book, 6th edition. Reynolds number is 22,500. Schmidt number mu for the air, that's where the diffusion is happening. Diffusivity 1 into 10 raised to minus 5. 1 into 10 raised to minus 5. Rho 1.2. Schmidt number is 1.67. Concentration boundary layer and momentum boundary layer are almost the same. 1.67. So if you substitute, you will find Sherwood number is 111.76, which means very large. So kg prime is 0.045 meters per second. Substitute that here. Qg integrate. You will find that length required is 9.6 meters. This is how the catalytic converters work. Engine exhaust contains unreacted hydrocarbons, carbon monoxide, NOx. Catalyst is coated on the wall, platinum catalyst, alumina is the wall, and it's a multi-channel. It's not just one pipe. There are multiple pipes. They're not circular pipe. They're rectangular. It's called as a honeycomb. That honeycomb like this. The catalytic converter in cars. That's how it looks like. There is a pipe, exhaust pipe, and inside that exhaust pipe there is a catalytic converter made of channels of alumina Al2O3 on which platinum is coated. And exhaust gas flows through each of these channels perpendicularly to the screen, goes into the screen, and then it reacts. So obviously we are just looking at one simple pipe, one pipe out of this honeycomb. catalytic. That's how catalytic converter works. And this concentration changing with respect to distance is called as plug flow. Plug flow. Plug flow. Okay, just to sometimes we use these kinds of expression, but we put them slightly differently. It will help you in the next problem. So ln C in by C out is kg prime pi dl by qg. So pi dl is the surface area of the pipe, right? I can divide by volume of the pipe and multiply by volume of the pipe. Let's say V is the volume of the pipe, not velocity now. V is the volume of the pipe, right? Velocity we are denoting as Vg, if you like. Where was it? Velocity. Yeah, this should be Vg. Okay, volume of the pipe. So this surface area per unit volume is a very important parameter. We are going to denote that by A bar. How much surface area is there per unit volume? Obviously, higher the surface area per unit volume, higher would be the mass transfer rate. So we are going to write this little differently. Qg would be kg prime A 1 by ln C in by C out into V. If I multiply both sides by C in minus C out, C in minus C out. The left hand side is what is the overall rate of mass transfer or overall rate of reaction, right? Overall rate of destruction, which is same as overall rate of reaction, which is same as overall rate of mass transfer. Right, overall rate of mass transfer. kGa, this quantity C in minus C out divided by ln C in by C out. We are going to call this as log mean concentration driving force. Log mean concentration driving force. So we are going to write rate, and kGa we call as volumetric mass transfer coefficient. Kg prime has units of meters per second. A prime has units of meter square per meter. A bar, A under bar, meter square per meter cube. Surface area per unit volume. So kg prime A has units of 1 per second. We call this as volumetric mass transfer coefficient. It's like volumetric mass transfer rate. And if you're comparing reactions, 1 per second. If you're comparing reactions, if your reaction is to be fast, what we need reaction. How did we write reactions? Rate of reaction, K, rate constant, we had written in terms of 1 per second. So we can now compare rate constant versus this volumetric mass transfer coefficient. So if rate constant is very, very large as compared to this volumetric mass transfer coefficient kg prime A, then we will have this particular situation where the concentration at the surface is 0. If K is not large, so if you want to think in terms of the food analogy, this is the rate at which food comes to the table. This is the rate of consumption of the food. Okay? That's why we want to define in terms of volumetric mass transfer coefficient. So as you go along in your other courses, more and more times you will have to compare wherever mass transfer and reactions are happening. Okay, this equation we can write slightly differently as well. This equation, these two equations, we write it slightly differently. We write Qg into C in minus C out is equal to Kg prime A delta C log mean into surface area multiplied by, or S is the cross-sectional area multiplied by volume. V is the volume of the pipe. So S we are writing as cross-sectional area. So S is pi by 4 d square, not surface area, mind you. Pi by 4 d square cross-sectional area multiplied by L is the volume of the pipe. Okay. I can bring this Qg divided by Kga prime multiplied by C in minus C out divided by this delta C Lm. S I have brought on the other side, is Qg by S. It gives me length of the pipe. So this term is called as number of transfer units. This is how many times is this log mean concentration difference reduced by. It's called as number of transfer units, and this is called as a height of transfer unit. More about this in your next semester when you talk about other kinds of mass transfer operation. But I just wanted to make that point here because you're going to use it in the next semester. They are going to use this concept, number of transfer unit multiplied by height of transfer unit. You're going to use for mass transfer operations as well as heat transfer. Similar concept occurs in heat transfer as well, number of transfer unit and effectiveness or height of transfer unit, NTU epsilon. So let's not think about that just now. We will see as we go along. Here's the next problem. So a packed bed consists of a tube 50 mm ID packed with spherical catalyst, each of 6 mm diameter. Bed voidage is 0.6. Density of the catalyst particle is 2000. Gas phase contains the reactant A, flows through the packed bed at a superficial velocity of 1 meter per second. A reacts on the solid surface at a very fast rate. The rate of reaction of A on the surface of the particle is so fast that concentration of A at the surface of the catalyst can be assumed to be 0. Same as the previous case. Instead of pipe, now it is particles. So calculate the length of the tube required to achieve 99% conversion of A. Assume that the properties of gas are density 2 kg per meter cube, viscosity 1 into 10 raised to minus 5, molecular diffusivity 1 into 10 raised to minus 5. The reactor is operated at steady state. Solve this problem. Pause the video, solve this problem. You should be able to solve this on your own now. Here's the solution. Okay, first of all, draw a physical picture. Should you take macroscopic or a microscopic balance? Where is mass transfer occurring? What is the driving force? Does concentration of A vary with distance or with time? With distance, the problem that we saw previously. With time, the problem that we saw in previous lecture. Sugar, drug, tablet dissolving. Okay. Problem yourself. You should be able to do it on your own now. Pause the video. Here's the solution. So imagine this is the bed. We are going to take Z and Z plus delta Z, and we are going to take this control volume. We are going to take this as a control volume, and we are going to write balance. Where is the mass transfer occurring? Imagine particles. Imagine these are the particles. These are the particles. Gas is flowing like this around. So if you think about this is the catalyst, there is a boundary layer. Gas is flowing. There is a bulk concentration. There is concentration A0. Mass is being transferred. A is being transferred to the surface where it is consumed. So concentration of A near the surface is 0. Driving force is Ca minus 0. Like last problem. Now you should be able to solve. Pause the video, solve it for yourself. Here's the solution. Material balance in this control volume. Qg into Ca at Z in minus out is equal to rate of reaction is the same as rate of mass transfer. Same way as last time. ln Ca in minus by Ca out is Kg prime A Vg by L, superficial velocity. Right? Solve this for yourself. I need to know how do I get this Kg prime A? Correlations. So Thion's and Kramer's correlation for packed bed, if you see, this is the correlation. Sherwood number 1, Reynolds number, this is how Reynolds number is defined, Schmidt number. Solve this for yourself. Reynolds number 3000, Schmidt number 1. Oh, sorry, Schmidt number should be 0.5. Density is 2. Oh, make this correction. This should be 0.5. Okay, this just cancels. 1 by 2.5. Okay, make that correction. Sherwood number, you may get slightly different value because I have taken Schmidt number raised to 1 by 3. So 1 raised to 1 by 3 versus 0.5 raised to 1 by 3. That's how your answer may change slightly. But Kg prime is 0.061. So slightly it may change. Interfacial area is 6 epsilon by dp. So if it's a spherical particle, interfacial area is 6 by dp. Why we are multiplying by epsilon s is because we want interfacial area per unit reactor volume. Reactor volume. I want to find reactor length. Tube is the reactor. So think about this, where this comes from, right? Just logic. So interfacial area is 400 meters square per meter cube. This is square. It's not very clear in the thing, but it is 400. So for 99% conversion, all I have to do is substitute the values. L will be 0.19 meters. Get this for yourself. Make sure you've got this value. You may get a slightly different value because the Schmidt number is slightly wrong I had taken, so that's okay. Again, some considerations for your later courses. Many reactions are not so fast. They require longer tube lengths, right? So reaction does not take place on this entire surface. Catalyst contains active sites. Let's say platinum. That's where reaction is happening. Platinum is not going to be across the whole surface. Platinum is going to be only in selected places on the surface, right? So that's where the reaction is occurring. Number of active sites per unit surface area therefore is a critical parameter. And sometimes these catalysts are porous. There are active sites inside the pores as well. So that means now reactant has to diffuse inside the pores of the catalyst and then react. Small changes. Why these things are coming? Catalyst can be porous. So what is the overall step? What is the overall reaction? The reactant has to diffuse to the surface. It diffuses inside the pores and then reacts. So these three are simultaneous. So all these things are required now. When you go to your higher and higher classes, other classes, you will have all these three. When you start doing reaction engineering, all these things are important. So mass transfer by diffusion to the surface or diffusion inside is a prerequisite for that course. That's why we are doing mass transfer now. Therefore, you need to understand all these concepts because they are going to be required for us to function as a chemical engineer. We are going to design reactors. We are going to design catalytic reactors. That's why all these concepts are required. Okay, little bit about Fick's law. Imagine that there are two containers. One contains A and one contains B. So blue molecules and red molecules, and these molecules are in thermal motion, random thermal motion. Now this partition we are going to remove. What happens now? There is no bulk flow, only purely diffusion. So A is going to diffuse from left to right, B is going to diffuse from right to left, purely diffusion. Now let's say the flux of A we call as NA, that is going towards the right. A is diffusing to the right, B is diffusing to the left. NA is the flux of A, NB is the flux of B. It is purely by molecular motion, no bulk motion. But what is bulk motion? Bulk motion is nothing but bunch of molecules traveling in one direction. Think about that. Fan, bulk motion. All molecules of air traveling in the downward direction. So molecular motion itself is a one direction, is itself a bulk motion. Net flux, suppose 500 molecules are traveling from left to right, 300 molecules are traveling from right to left. What is the net transfer? It's 200 molecules to the right. So the total flux is just Na plus Nb. And total flux, that 200 molecules traveling from left to right, is nothing but bulk motion. So now the flux of A is because of the bulk motion. Bulk motion is arising out of Na and Nb put together. Na plus Nb is a net flux. So if you think about a gas mixture, let's say in a gas mixture there are, in a gas mixture, let's say there are two things, A and B, and at any point of time, at any location, let's say Ya is the mole fraction of A and Yb is the mole fraction of B. So Ya would be concentration of A divided by total concentration, which is same as Pa by Pt. Mole fraction of B is same as Pb by Pt. So flux of A due to bulk motion, suppose there are 200 molecules going from left to right. This is 500. Suppose this was 500. and suppose this was 300. That means there is a net flux of 200. That's the bulk motion. Bulk molecules traveling in the same direction, and in t is 200 to the right. So if 200 molecules are traveling to the right, out of these 200 molecules, how many molecules of A are traveling to the right? It is 200 multiplied by mole fraction. Think about this. So flux of A due to molecular motion purely, if I say J, the net flux of A is that due to bulk motion NT multiplied by YA plus JA. So it is NT multiplied by YA minus DAB into DCA by DZ. Same way if I write NB, it is NT multiplied by YB plus JB. It is NT multiplied by YB multiplied by minus DBA. Look at these two, they are different. It is DAB and DBA. Diffusivity for A in B and diffusivity for B in A. Diffusivity for blue molecules in a red medium or diffusivity of red molecules in the blue medium. That's what these are. If you just add them up, you will get JA is equal to minus JB. So in other words, you will get DAB as DBA. Diffusivities of A in B and B in A are identical. Okay, that's first result. Second, sometimes we have diffusion of A through stagnant B. Means overall, if I am an outside observer, observing this screen, as if molecules of B are not moving, outside observer. That is the meaning of stagnant B. Why that happens? Let's look at this. The moles flux of A is NTYA minus DAB DCA by DZ. So NA is equal to NA plus NB into YA minus DAB into DCA by DZ. If B is stagnant, means NB is 0. So NA multiplied by YA, NA is equal to NAYA minus DAB DCA by DZ. So NA would be NA into 1 minus YA would be minus DAB into DCA by DZ. Convection can be related to diffusion. So if you want to imagine, let's imagine a situation that partial pressure of A is higher here, partial pressure of A is lower here. PA1 is higher than PA2. Now if total pressure is the same, PB1 will be lower than PB2 because total pressure is the same. Total pressure must be equal to partial pressure of A plus B. Total pressure must be equal to partial pressure of A plus B. So let's say here at this location, let's say A is getting consumed, A is reacting, B is not reacting. Let's say A is reacting, right? So there is a driving force for A. That driving force for A sets up a driving force for B. PB2 is higher than PBA. The driving force for B is in the opposite direction. Driving force, but that driving force for B will lead to motion, diffusion of B, but there is a net transfer of A. That net transfer of A is a bulk motion. B will be carried towards the wall where reaction is happening because of bulk motion. So for B there are two motions. One is diffusion of B from right to left because of the driving force. But there is a bulk motion of B because of there is a net motion of A. Bulk motion of B is going to take B from left to right. Think about this. These are important concepts. These are difficult concepts. You need to think a lot. You need to visualize. So motion of B is in two different directions because of diffusion and because of bulk motion. That leads, if these two are equal, because there is no net consumption of B, these two have to be equal, that leads to a stagnant B. As if for an outside observer, B molecules are not moving, B is stagnant, B is not diffusing, but in reality it is diffusing from right to left by molecular diffusion, but it is taken by A along with it by the bulk motion because of the net transfer of A. As if these two processes are occurring at exactly the same rate. They have to occur at exactly the same rate because there is no net transfer of B. B is not reacting, so there is no net transfer of B. So these two processes are exactly the same rate. That's why for an outside observer, they observes as if B is stagnant. Integrate. It's just a matter of maths now. Just integrate, and you call this as log mean driving force. You can see that for yourself. That's straightforward. Just maths I have given you. So the flux of A is DAB CT total concentration YB2 minus YB1 divided by log YB2 by YB1 into YB2 by YB1 Z2 minus Z1. I can combine these either in terms of partial pressures or mole fractions or in terms of the total concentration. Either way I can write. Oops, let me just rub this. I've already taken that into account. So this, whatever I have circled, that part we call as log mean concentration of B. Look at how we had defined log mean concentration in the earlier problem. That's why I wanted to bring that concept here. Log mean concentration driving force. Here it is log mean concentration driving force for B. Okay, so you'll get this as a flux. Some examples where this is important. Okay, let's say absorption of A from a concentrated gas stream. So let's say we have, let's say ammonia, and A is ammonia, B is air. Ammonia is in air. It's a pollutant, toxic. So we want to scrub that ammonia with an acid. So ammonia reacts. Let's say there is HCl here. Ammonia reacts, but air does not react. Air diffuses and air is convected. Air is stagnant. Diffusion of A through stagnant B, or condensation in presence of non-condensable gas. Let's say we have a steam and air mixture. A is steam, B is air. And let's say we have a cold surface here. Steam will condense, means partial pressure will reduce, right? Means there is a driving force for steam, but air builds up near this surface where condensation is occurring. So air diffuses, air is convected, stagnant air, right? Or concentration polarization in gas separations or membrane separations. So membrane separation you will do in your later years. But imagine that there is a membrane here. Imagine there is a membrane here, right? So then let's say there is water here, right? And we want to purify that water. So we have a solution. We have water plus some dissolved salts or some dissolved organics. Okay, we want water to come out here, but salts we don't want to come, or pollutants or higher molecular weight compounds, particles. Maybe molecular weight, maybe organics, maybe polymers, maybe proteins, maybe enzymes. We don't want them to go through the membrane. We want to purify that water. Okay. So membrane near the membrane, we have a high concentration of that salt or high concentration of that protein. There is a driving force for that protein in the back direction. Bulk motion. What liquid water is taking, as it is filtered, it is taking the protein to the surface. As if to an outside observer, the protein is stagnant. Diffusion of water through a stagnant medium of protein. Okay. Or evaporation of liquid from a surface into a gas stream. Just to note, if mixture is dilute, then CT is same as CB log mean. These concepts are important. I'm just saying these sentences, but unless each and every sentence you understand, don't go forward. Okay? I'm just making some sentences. Unless you understand these concepts, don't go forward. Understand everything that is written on the slide. Derive for yourself. Only then go forward. Okay? How this CT is equal to CB log mean? understand, and then go forward. So Na would be, this is like the normal Fick's law that we saw in our earlier class. Na is minus dA minus molecular diffusivity dCA by dx, or dCA by dz if you like. Yes, we used, but we used it unknowingly, unaware of these complications, unaware that these things happen if the concentration of A is large. Only if the concentration of A is dilute, then you are allowed to write Fick's law like this. Else you have to write Fick's law like this. Else you have to write Fick's law like this. Where was that? Here. Okay, here is a problem. So there is a tube that contains a liquid. Let's say it's acetone. So acetone has a high vapor pressure here. There is an air flow. So partial pressure of acetone is 0. So now there is a driving force for acetone to diffuse through this air. Right? Air, partial pressure of acetone is 0 here. Partial pressure of air is total pressure. Partial pressure of acetone here is equal to vapor pressure. Partial pressure of air is 760 minus vapor pressure, or total pressure minus vapor pressure. So there is a driving force. So acetone is diffusing through this stagnant air. Stagnant B, diffusion of A through stagnant B. Diffusion of A through stagnant B. Air has a driving force in the downward direction, but bulk motion of acetone is taking air upwards. These two are opposing each other, and they oppose each other exactly same rate because air is not moving, air is not going into the liquid layer. So they cancel out, as if for an outside observer air is stagnant, but in reality it is moving in opposite directions. Okay, so here is a problem. You can see the problem, you can read the problem for yourself. Total pressure is, let's say, 101.33 kP. PA1, vapor pressure of acetone, 30 degrees centigrade, 37.64 from Antoine equation. PA2, high airflow rate, so partial pressure of acetone is 0 at location 2. So now there is a PB1 is 101.33 minus 37, 63.69. PB2, total pressure 101.33 kPa. Let's say density of liquid acetone is 780. Liquid level reduces by 0.05 centimeters in 30 minutes. So if I do this experiment over a long period of time, acetone diffuses, the liquid level drops by with time. So after 10 minutes is like this, after 20 minutes like this, 30 minutes like this. So after 30 minutes, liquid level is reducing by 0.05 centimeters. So length of the tube between the top liquid level to the top of the tube is, let's say, 25 centimeters. Calculate diffusivity of acetone in vapor in air. So solve it for yourself. Solve it for yourself. Use this expression. Use this expression. What are the things that we know here? Solve it for yourself. Pause the video. Here's the solution. Right? What do we know here? What do we know here? CT we can calculate, total pressure divided by RT. CB log mean we can calculate. CA2 we know, CA1 we know, Z2 we know, Z1 we know. Right? If I can calculate flux of A, flux of acetone, we can calculate diffusivity. That's what I'm asking in this problem. Okay, let's calculate. Let's calculate. Let's just make a small change, small correction. There is a small error that I have made. Right, 780 is the density. Right, so CT we can calculate, CA1 minus CA2 we can calculate, CB1 we can calculate, CB2 we can calculate. So CB log mean we can calculate. Z2 minus Z1, right? Liquid level is hardly changing, it's 25 centimeters. Practically constant with respect to. Now Na, if I have to calculate, what is Na? Is the flux of A, is how many moles of A are diffusing per meter square per unit time. How will I get that? Liquid level is dropping by 5 centimeters, 0.05 centimeters, sorry, 0.05 centimeters. So if I multiply that by density, so 0.05 centimeters is 0.5 millimeters. Okay. It changes in 30 minutes, means 1800 seconds. So 0.05, so this is meters multiplied by kilograms per meter cube density. If you don't like that, multiply by cross-sectional area of the tube. Cross-sectional area of the tube. Let's say S is the cross-sectional area of the tube. So S into change of height is the volume of acetone that has evaporated. Multiplied by density, that will give you, so multiplied by density, that will give you mass of acetone that has evaporated. It has evaporated through that cross-sectional area S. That gives you flux of acetone per unit time. Right? Understand this. Understand this. How flux is this? It is just simply based on mass balance. That's why that MEBC course, you should be 100% confident. So molar flux of acetone is this divided by 58. So it will get 3.75 to 10 raised to minus 6 kilomoles per meter square second. So now I get this. I can get DAB as 5.03 into 10 raised to minus 5 meters square per second. There is an experiment that you are going to do. You are going to measure time, and you are going to measure the change in height with respect to time, change in the liquid level with respect to time. That's going to allow you to, so after 10 minutes is like this, 20 minutes, 30 minutes. This is just an exaggerated picture. The change is very small because diffusivity is small, right? Okay. So you are going to do this experiment. Actually, you are going to measure the liquid level in a certain period of time, and you are going to back calculate diffusivity using this formula. Understand all these things, understand the calculations, understand the concepts, then only go forward. These are very, very important concepts that we are talking about. They are difficult to comprehend, they are difficult to understand. Some of these concepts are difficult to comprehend because it is difficult to visualize. It is difficult to visualize. Therefore, you need to spend time, you need to read, you need to digest, you need to solve problems. Then only you will be able to comprehend. All these concepts are going to be required later on. Later on, for you to function effectively as a chemical engineer, all these concepts are required. Mass transfer, chemical reaction, driving force, resistance, mass transfer coefficient. How do I estimate those mass transfer coefficients? Everything you are going to require. Everything you are going to require. Right? Understand, take time. These are difficult concepts. Take time, visualize, assimilate. Here's the next problem. Sometimes you have equimolar counter diffusion, meaning diffusion of A, flux of A because of diffusion of A, and flux of B because of diffusion of B are exactly opposite. Why that will happen is if A, both there is a consumption of A as well as consumption of B. So this happens when you start talking about distillation. More volatile component transfers from liquid to vapor, less volatile component transfers from vapor to liquid. This is across the two phases as well, right? So then Na is equal to Nb. Then you get flux of A is just purely as if it's a normal fixed law. Okay? You will study this later on when you start doing distillation, equimolar counter diffusion. Okay? Here's the next problem. Imagine that there is a slab. Okay? Slab is like this. Let's say that slab contains A. Let's say concentration of A in the slab initially at T equal to 0 is this CAI. At some instant of time at T equal to 0, we are going to make surface concentration less than CAS, let's say. Okay? CAS could be 0. Okay? But we just some small value right now. Now diffusivity of A in the matrix is dA. So due to this concentration gradient of A, so Ca is going to diffuse from inside this matrix, inside this solid to the surface, and as it diffuses, the concentration of A drops inside this matrix as a function of time. Okay, I want you to write an expression for how Ca varies within the slab as a function of x the distance, and T. What are the applications? Drug delivery from a polymer matrix. Imagine this the polymer matrix. It's a patch that you keep on the skin. Drug diffuses inside the skin. Your skin is here. Let's say either side, or let's say even one side. Skin is here. So drug diffuses, and as it diffuses, it goes inside the skin. Concentration of the drug inside the patch reduces. Or membrane synthesis. Suppose you want to make a membrane, you have a polymer dissolved in a solvent, you put that polymer solution in an anti-solvent, or you expose it to anti-solvent. The solvent diffuses, and as the solvent diffuses, the solid polymer precipitates, and you make a membrane. That's how membranes are made. Okay. Or drying of products. Imagine that this is a, let's say, some matrix, let's say paper or wood, and it is wet right now, so there is a concentration for water vapor inside this matrix, and you expose to hot air. Concentration of water vapor is 0, so the water vapor diffuses from inside. As it diffuses, the amount of water vapor in the wood or paper reduces, and it dries. Right? So very important applications. Right? As a first step, I want you to qualitatively draw how Ca will change with respect to x and t. Draw that. Pause the video. Draw. Here is the solution. Okay, if this is the matrix, this is how the concentration will reduce with respect to time. So Cas and location with respect to x. This is at t equal to 0. With time, as time goes up, concentration inside the slab, inside that solid, reduces, and it's symmetric. So we are only showing the half slab. Okay, solid matrix. What methodology we would like to adopt? What methodology we would like to adopt? Flow is laminar, no flow situation. Definitely go for this. Definitely not turbulent. Definitely we should not go for microscopic when we can do with a microscopic balance. Okay, here is the answer. You should get this. This is a first order differential equation with respect to time, and a second order differential equation with respect to x. I need one initial condition with respect to time, that is t equal to 0. Ca everywhere is equal to Cai. This is for all x. It is one dimensional diffusion, transient, unsteady state. Boundary condition with respect to x, for all t greater than 0, dCA by dx is 0 at x equal to 0. Symmetry condition. Ca is equal to Cas at x equal to L. Okay. Let's make this dimensionless. Let's make this equation dimensionless. Let's define eta as x by L. Theta is equal to Ca minus Cas divided by Cai minus Cas. So our initial condition would become t equal to 0, theta equal to 1. Ca is Cai minus Cas, Cai minus Cas. Theta is equal to 1 at t equal to 0. For t greater than 0, d theta by d eta is equal to 0 at eta equal to 0, and theta is equal to 0 at eta equal to 1. So our equation now becomes like this: del theta by del t is equal to dA by L square del square theta by del eta square. Get this for yourself. Unless you get this, don't go forward. Clear your concepts now. I would like to make time also dimensionless. Let's bring this L square here, dA here, rearrange. T dA by L square. So T dA by L square is a dimensionless time. Let's call it as tau. T is in seconds, dA is in meter square per second, L square is in meter square. It's a dimensionless time. So our equation becomes like this now. Del theta by del tau is equal to del square theta by del eta square. These are the boundary conditions and initial condition with respect to tau. Initial condition with respect to tau, at tau equal to 0, theta is equal to 1. At tau greater than 0, d theta by d eta is equal to 0 at eta equal to 0. Theta is equal to 0 at eta equal to 1. I am writing this very quickly, but unless and until you understand this, we have done momentum balance and all these conditions we have seen, symmetry, no surface conditions, all these we have seen, so it should be very clear to you now. You might have seen in your maths course how to solve this as a function of time by separation of variables. We propose that theta is equal to some function of eta and some another function of tau, and rearrange this to get this equation. And we will say this is independent of g, this is independent of f, therefore it must be a constant. Let's call that constant as minus lambda square. Reason for lambda square and reason for minus in a short while. Solve this. You must have solved it in maths. Solve it again for yourself. Okay, revise your maths. Do it for yourself. Pause the video. Here is the solution. Okay. Reason we do minus lambda square is then because we can write it as a sine lambda eta plus b cos lambda eta. If you put the first boundary condition at equal to 0, you will find that a is 0. So f becomes b cos lambda eta. Second boundary condition, if eta is equal to 1, f is 0. So b cos lambda must be 0. So lambda must be pi by 2 or 3 pi by 2 or 5 pi by 2. You can write it as lambda equal to 2n minus 1 upon 2 into pi for n equal to 1, 2, 3, or in other you can say lambda is equal to pi into 2n plus 1 by 2 for for n is equal to 0, 1, 2, 3. Either way, choice is yours. So f would be summation of n equal to 0 to infinity bn cos lambda n eta. This can be a summation because all such terms will satisfy this condition. That's why we are writing it as sum. And bn, those many n's will be required. Right? Lambda is defined as this. Second part, dg by dt is minus lambda square g. So we will get g is equal to e raised to minus lambda square by t. So g will reduce as a function of time. That's why we take that minus sign. It converges. Theta is not exponentially reducing. Theta is reducing. So g must reduce with tau. Concentration is reducing with time. So g must reduce with tau. So minus sign we have taken here. Understand? So theta would be this. Now use initial condition, tau equal to 0, theta is equal to 0, theta is equal to 1, sorry. E raised to 0, that's 1. Right? So 1 is equal to summation n equal to 0 to infinity bn cos lambda n eta. This allows us to get value of bn. So if I multiply by cos lambda m and integrate, right? Fourier series, right? Understand separation of variables. You've done this in your class, in your maths class, right? So you'll get bn values. If not, this is how you are going to get it. So this is the final solution, theta. Plot theta as a function of eta for different values of tau. Take tau equal to 0.05, 0.1, 0.15, 0.2 and so on. Use Excel. Plot this for yourself. Pause the video. Don't go forward, for heaven's sake, unless you solve. Unless all this is clear to you, don't solve. I am assuming that this is clear to you. Plot. This is how concentration will look like with respect to time in terms of theta versus eta. Tau equal to 0.05, tau equal to 0.1, tau equal to 0.2, tau equal to 0.4, tau equal to 0.6, tau equal to 0.8, tau equal to 0.9, tau equal to 0.1. Sorry, not 0.1, 1. This is how it is going to look like. Okay, what do I want? What do I want to find? First of all, find an expression of how Ca varies with time. You got that? Something more from here. This is how concentration is going to vary with time and location. Something more from that. Look at the tau value of 1. At tau equal to 1, almost all the concentration has become equal to the surface concentration. Practically everything has diffused out of that medium. So tau equal to 1 is going to tell us how much time is required for diffusion to occur. Okay? Call that as diffusion time scale. In other words, concentration profile becomes nearly flat when tau is almost 1. That's the time scale for diffusion. If you want, we have already made this dimensionless. This is of the order 0 to 1. This is of the order 0 to 1. Only way this is of the order of 0 to 1, theta is of the order of 0 to 1. Only way this can happen is when tau varies from 0 to 1. For tau to vary from 0 to 1, this t by L squared by dA has to vary from 0 to 1. So correct scaling parameter for time is L square by dA. Only then this term will become 0 to 1. We call that as scaling. Remember, we scaled our boundary layer equations. We got Reynolds number, we got thickness of boundary layer. Now the scaling parameter for time is L square by dA. This is the diffusion time scale. Unit is seconds. Right? Or rate of diffusion, if you want, it's 1 by time scale. dA by L square. Unit is second. Similarly, we can think of 1D conduction. Del T by del T is alpha del square T by del X square. This can be made dimensionless. Del theta by del T by L square by alpha. Tau. Right? Or conduction. L square by alpha. You might have studied this somewhere. Okay. So if you want to say, for example, you want to dry wooden slabs 1 centimeter half width, and diffusivity of water vapor in the wood is, let's say, 10 raised to minus 9 meter square per second. Time scale for drying would be L square by diffusivity. L square 0.01 square divided by diffusivity. Oops, it's not 10, it's 10 raised to, whoa. Let's pause. Correction. It is not 105. Oops, it has still become 105. Why is that? It's 10 raised to 5. Yeah, now it is correct. Sorry for that error. Right. So time scale for drying is 10 raised to 5 seconds. 10 raised to 5 seconds. That's 27 hours. So that's why wood and all these things are very difficult to dry. They are kept in a hot environment for a long time. They are dried slowly. Diffusion dries them. Okay, that's the importance. Now, some more points. Time scale for conduction, like diffusion, is L square by alpha. Time required for temperature to become nearly uniform by conduction. We're going to use this when we start doing heat transfer. In conduction, the dimensionless time alpha T by L square is called as Fourier number. Same way, diffusivity T by L square, we can call it as Fourier number for mass transfer. So this, let's look at this. Suppose there is diffusion and reaction happening simultaneously, like in a catalyst particle. Diffusion is happening inside the pore, reaction is happening inside the pore. So the rate of diffusion, scale for rate of diffusion is dA by L square. And if I say K is the rate of reaction, that also is second inverse. Now I can compare dA by L square and K. So dA by L square, if I compare diffusion rate versus K, I will get relative importance of mass reaction versus diffusion. In fact, we are going to define a parameter K, rate constant, divided by dA by L square, or we can write it as K L square by dA. This is a very important number. It's a dimensionless number. It compares two scales. Reaction time scale or reaction rate and diffusion rate. That helps you to simplify diffusion and reaction problems. Okay? More of it is in third year. Okay. So whatever we have discussed so far is from this book for you to read. Chapter 30, we talked about different kinds of mass transfer coefficient scenarios. Chapter 26, section 26.1 tells you about Fick's law, diffusion of A through stagnant B. Chapter 27 talks about these unsteady state diffusion and diffusion time scale and so on and so forth. Okay. Very important point. All these things that we have done, you should be conversant with all these things. Some of these concepts that we have talked about are not straightforward. take time to understand, take time to digest. We require them to function as a chemical engineer. Only when you have these concepts, you are 100% chemical engineer. You can become 100% chemical engineer just in the second year. These concepts, just next year, third year, fourth year, just going to be application of all of these concepts to different situations, to reactions, to catalysis, to biology, and other applications, separations, membranes, and so on. Okay, these are important concepts. Take time to understand, digest, read, solve problems. Only then you will be able to understand all these things properly.